Hey kids, it's Creepy Baby, and I'm about to go for a ride. Whee! Ah, the projectile! In this episode of the podcast, we want to look at centripetal forces as it applies to something that's being swung in a vertical circle. We want to look at the forces at a couple points: at the bottom of the swing, in the middle of the swing, and at the top of the swing. We're going to actually do some math with the bottom of the swing and top of the swing. Now, the print on this problem I'm working off of is going to be a little too small to read in the video. So if you go to the class website, jedokhs.pbworks.com, you can download a copy of this problem to follow along with. But I'll make sure as we go along I'm reading out the questions, and so you can tell what's going on if you are just watching the video. In part A, we want to analyze the forces at work in this vertical swing. We've got a mass M being swung in a vertical circle, and so when we ask ourselves what's providing the centripetal force, remember centripetal force causes objects to move around circles or curves. The centripetal force is being provided by the tension. And so on these two figures we want to look at the forces at point P, which is right here in the swing, and at point Q at the bottom of the swing. Now we know that centripetal force always points towards the center of a circle or a curve. So the tension is going to point towards the center. We'll label that vector T. And weight always points downwards. So there's our forces at point P. At point Q, tension again points towards the center of the circle. And as always, weight points straight down. So as you can see, the direction of the weight never changes, but since the tension is providing a centripetal force, the tension always points towards the center of the circle. In part B, we want to find the minimum speed you can spin the mass with so that you'll still make a circle and it won't fall off of the circle. So what we've got to realize here is we've got to look at point Z, because if something's going to go wrong, it's going to fall off at point Z. Now, if you're swinging with more than enough speed, if you're really going as fast as you can, tension is going to point downwards towards the center of the circle, along with mg. Both forces will point downwards there. So if I were to draw a free body diagram separately here, we'd have tension going down, mg going down. And we'd say at point Z, if F equals ma, we know that since we're dealing with a circular situation, the acceleration is centripetal acceleration. So that would be v squared over r. And when we look at the forces in a centripetal problem, forces that point towards the center are positive, and forces that point away from the center are negative. Now at point Z, both forces point towards the center, and so they would be added. So T plus mg equals mv squared over r. However, if we're looking at the minimum speed that it takes to get around the circle, what's going to happen is that the tension is going to be reduced all the way to zero. The faster you swing, the more tension there would be. The slower you swing, the less tension is required to pull your object around the circle, to the point where at your minimum speed, the tension becomes zero. So that's the trick to finding the minimum speed. Well, at this point then, all we have to do is solve for v. We notice that the masses cancel out, and so moving r to the other side of the equation, we get gr equals v squared. And so if I take a square root of both sides, we get that the minimum velocity is the square root of g times the radius. In part C, what we want to know is what's the fastest you can swing without braking. And so we're given that the force, the maximum tension you can have, is T max. And so what we have to do again is set up our force equation, but we want to set it up at point Q. At point Q, we see that tension points towards the center of the circle, weight points away from the center of the circle. So when we say F equals ma, this is going to be T minus mg. Tension being a positive force that points towards the center of the circle, weight being a negative force pointing away from the center of the circle. And again, since this is a centripetal problem, the acceleration becomes mv squared over r. So that recognition of this being, seeing the circles, seeing the circular motion, and recognizing this as a centripetal problem is key. What we want to do here then is, again, solve this equation for v, and t becomes T max. Now, a lot of times when we're doing these alphabet soup problems, we saw in part B, the math condensed down to a nice, simple, final answer. Well, this time the algebra is going to get a little messy, but we just need to take what we have and solve for v in terms of everything else. T max is a given value, so that's okay to use. M is a given value from the beginning of the problem. G is a constant, and so these things are all okay to use, and don't be put off by the fact that we're going to get a messy answer out of this. So if I multiply both sides times r, I'm just going to put r and put this entire side in parentheses, T minus mg, and that's T max, by the way, and that'll equal mv squared. Divide both sides by m, and I'm just going to, again, leave that outside the parentheses, and then take a big square root of the thing, and again, it's ugly, but it's the right answer. I'll come over here and rewrite it. V is going to equal big old square root sign r over m times the quantity T max minus mg. Now you can divide the m through here and do some more algebra with it, but you've got an expression for v in terms of the given variables, and that's all you need. As we look at part D, it says, suppose that the string breaks at point P. Describe the motion of the ball immediately after the string breaks. Well, you got to keep in mind that even though we don't have a velocity vector drawn into the picture here, because you don't want to include velocity vectors in free body diagrams, I can come over here and redraw the picture. Point P is at this point right here at 9 o'clock. Remember that the velocity vector stays tangent to the circle at all points. The acceleration vector points to the center in these situations. Well, if the string breaks right here, an object in motion will tend to stay in motion the way that it's going. And so what we want to say is that the ball travels straight up and then will behave as a projectile and come straight down under the influence of gravity. And this may be a little more than they may be looking for, but what we're doing is we're doing a complete description of the physics. Be careful and don't say anything wrong after you've said the right answer. But the fact of the matter is there's going to be no more horizontal motion because of this point. We've got a velocity vector that goes this way, and object in motion will tend to stay in motion, and you'll come straight up and then straight down as a projectile.